Yes. Yes, in fact, I've already posted on Canvas. I've already posted on Canvas. So take a look there. But I'm not talking about it. Okay, here, okay. Shall we start? So, welcome back. Now the fun starts. Now the fall break is over. So, because it hasn't already been fun. So, what I'd like to talk about for a few minutes is the interim project report that, as you know, is due in a few days. You don't have to submit a lot, just a few pages. And as I promised, I'm going to do my own project along with you all, but submit these a little bit earlier. And so I've prepared my not one page, but as you'll see, short page report. And I would like you to follow basically the same format. In fact, you could take the text file, just remove my text and put your text in, that would be fine too. Okay, so you don't have to worry too much with latex futzing around. You may need some, if you're not used to using BibTeX, there's a bit of, note about how you might do that, but it shouldn't be too hard. Again, post questions quickly if you have any things. So how does the report supposed to look? Let me show you the report. It's also detailed in here. So, this is the report that we're going to be working with. Let me make it a bit bigger. Okay, so, you need a title. You need the name of the author, you need names of your group members. These are my two group members here. So, the report is going to be very short. As you can see, it's basically 2 pages. And then there's a reference section. Okay, so that's all there is to it. So you don't do a lot. What you need to do is provide, and I'll explain this in more detail, some background, what the paper is supposed to be about, and what your plan of action is. Okay, so let me explain this. So, you may not remember all the details from this paper that I talked about, but it was about these things called semi-definite hierarchies and approximation algorithms, and a lot of words there. I went through a little bit of it of how you might know what understanding these words. And again, you probably don't remember all of them right now, but that's okay. I'm just going to talk about this here. So, what I wanted to, the first part of your report will be background. Okay, so what is the stuff that one might want to know before reading this paper? Some of which you probably already discovered yourself, and some of more things you may still have to discover. Again, this is an interim report. I don't expect you to have all the answers right now. So, in particular, this paper is about, one of the things this paper is about is approximation algorithms. So, it might be good to introduce what that is. So, as you can see, I'm saying, when we show problems of NP hard, the next step is determine where you can find an approximation. Right? And so, that's the first sort of bit of thing. And now, it turns out that to understand this thing called semi-definite programming and its relaxations, you need to understand this other thing called linear programming, something I'm going to talk about very soon. And so I mentioned that in the report there. One method of finding some approximation that's specified on linear program, and so on, so on, so forth. Then the next bit of background you would need if you were trying to read this paper is what is a semi-definite thing? And so I spent some time writing down what I understood to be semi-definite programming. You can see here that I mentioned the citation here. This is actually a collection of lecture notes. Because if I don't know anything about semi-definite programming, I need to find out something about it. So I went and Googled. I found some nice lecture notes on semi-definite programming. And I linked to them. In fact, you can click on that too if you want to see. But that's going to happen a lot. You're going to find some information you're not very familiar with. You're going to look around. You're going to find a Wikipedia link. You're going to find some lecture notes. Lecture notes are actually quite good for this kind of thing. So I recommend you use them if you can. And then cite them. So that's what I said here. I've learned something about semi-definite programming. I've given a citation for where I found all this stuff. And then I wrote this up here. Okay, it's not, there's some formalism, but I'm trying to explain to myself and to the audience where this is coming from. Then a bit more setup. Okay, so why do we care about this thing called a semi-definite program? Well, it may be useful to find approximation algorithms, as we said before. And some problems here, cite. And this is taken more or less from this paper itself. For some problems, it's also the best known bound, but other problems you cannot bridge a gap, and this is where this paper comes in. So the background section sets the stage for what this paper is about. It's providing a microcosm of the context of why this paper is interesting. Of course, part of your report, your final report, is to really understand the background. So you're not going to get all that now. You're going to get a very basic set of things now. And as you see in the plan, there will be things that you need to do to understand the background better. But this is what the purpose of the background is, to set up the stage for understanding what this paper is doing. Then the next section, of course, is the main result. This paper studies what appear to be a generalization of seminar programs called seminar hierarchies. I don't know what these things are, but I'm just looking at words from the paper and said they're constructed by taking a program, somehow modifying it to get a stronger seminar program, and then solving that program, and then trying to recover a solution. And the big understanding I have right now is that this new one is somehow better than the old one, so I should get a better answer, and that's the hope. I don't know more about this yet. That's what I'm going to be reading about, and maybe you've read more, and that's good. Whatever you know at this point, is what you should put in. But this is what I understand by reading this paper, and that's what I'm going to put in here. And so another context, okay, so this is the hope. Prior work has shown that you can't do this, and so there are lots of negative results saying you cannot improve the approximation bound for an algorithm using these tricks, but this paper actually does something. It presents a positive result. So what this main thing is saying is that not only this is what it's doing, and this is why it's interesting. Okay, so the first paragraph was this is what it's doing. The second paragraph is saying this is why we should care about it. And that's very important. Right? Why should you care about the result they have? That shows the beginnings of some understanding of where the context of this paper is in the larger story of this area. So you do that. That isn't very big, that screen, I must say. Okay. I'm just curious, folks here, can you read that? People there, can you read that? No, you can't? Interesting. So, I mean, I'm just, yeah, this is quite big, but that's not that big at all. How many people can actually read anything on the screen? They just put this in. Okay, good number. Not interesting. Some people even hear me. Oh, okay. All right. Okay. Once you have some context for the background of the work and what the work is claiming to do, you now need a plan. Every paper needs a plan of attack. How are you going to break down this paper into little chunks that you can understand bit by bit to understand the paper? Again, I will emphasize, and you've probably seen this already, research papers are not stories. You don't read them from start to finish. You have to understand the different parts of the paper, figure out for each part what you need to know. So, the plan is this. We need to fully understand what a seminar hierarchy is. At this point, we're not quite sure we understand what it is. The explanation of the paper is there, but it's very terse. In order to understand hierarchies better, we will make use of these notes by this other person. Right. So I went and looked, and I found these nice little lecture notes on this topic, and I said, oh, I'm going to read those, and that's going to help me understand what a semi-definite hierarchy is before I can understand what this paper is doing. This is an interesting point here. We will focus our efforts on understanding the approximation algorithm for independent sets and hypergraphs. We will not cover tree coloring. So again, this paper has two results. It has a new approximation algorithm for this problem, independent sets and hypergraphs, whatever that means. It has a new result for tree coloring of graphs. I am deciding not to cover one and covering the other. This is a choice I'm making because, and I should have said this here, I feel that they're both using similar ideas, and one of them is hard enough already. Just understanding that's going to be very difficult. And so I prefer to focus my attention on that. I'm not saying that means you can arbitrarily jump like 9/10 of the paper you're reading. But I'm saying that you should make a strategic decision about where the main contribution, if the paper is basically saying, here's an idea, let's apply it to problem 1 and problem 2, then it's okay to say, okay, let's look at one of the two problems. If there's an idea that's interwoven in the paper, you can't just chop off half and say, okay, I'm going to stop understanding this now, because then you won't understand the idea at all. I have made the judgment that in this paper, this is how the paper is organized, that there is a basic idea and it's being applied to two problems, and therefore I've chosen this path to success. Okay? You are allowed to make that kind of decision, but make sure you make the right one. That's the catch. And you can always ask if you have a doubt. An important point again, okay, so a key reference for understanding their algorithm is this paper, this other algorithm is other paper, number 5, which is, presents an SDP for this problem, but as a weaker approximation. We need to understand this paper as well. So what is the point of this plan? The point of this plan is for you to show me that you've, well, read the paper, that you understand where the choke points are in your understanding, and you've laid out a plan to try and break those choke points. Without the plan, I don't know if you've read anything. It's entirely possible for you to essentially cut and paste stuff from the paper to generate the main result. You might be able to say something background, I doubt it, but you can say something without reading the paper very carefully. You will not be able to make a plan unless you at least skim the paper and try to understand where the holes are. And this is one of those things where you have to read without understanding in some sense. If you read a piece of text, you can't afford to wait till you understand every word in it. Then it will take too long. You have to get some high-level understanding of how the paper is put together. I talked about this in the lecture. That every paper has a certain structure. And the plan is going to show that you understand what the high-level structure is and where the parts are that need to be solved. Question?
So would section 2 be Could you think of that more as like the abstract, and section 1 would be like more general than the abstract?
I agree with the part about section 1 being more general than the abstract. Section 2 could be an abstract. However, a little bit more, how should I say, context helps. So for example here, I could have cut and pasted the abstract in the paper, but look at the sentences I have here, you know. Since the new semi-definite program is stronger than the original one, the hope is that this can give us a better approximation. This is actually not in the abstract of the paper. That paper assumes that the reader knows what they're doing.
Okay.
This is providing extra context that was not there in the abstract to say, well, this is why we want to do this.
Okay.
And that's where this is different from just a paper abstract. So paper abstract will basically say, this is our result and this is why it's awesome. As I've told you, you don't trust those things. What you want to know is this is the result and this is why I should care about it, not why the author thinks I should care. Sometimes they agree, sometimes they kind of. And sometimes you're spelling out things for yourself to understand how, to help you understand, and that's what you're going to put in your report. Yeah.
For the background, can we, you know, like if we have any references or anything, can we assume that they've been through this class and up to the point where we use VR? Like, are we writing this so that if one of our peers would look at it in time, or if somebody uses it in general?
Right, so what's your target audience? Is your target audience your peers, or your target audience me, or is your target audience some general researcher? Very good question. Who do you think the target audience is for this report that I've written so far?
Us?
No, no, let me rephrase, not who I think. Do you think that this is written for you? Or is it written for someone else? What do you all think?
For the peers.
Sorry?
For us.
In other words, do you find this something you can read? What I've written so far. That's the test, right? It's only written for you if you can actually make sense of it. If you can't make sense of it, it's not written for you. So that's a real question I'm asking. Do you find that this is accessible material for people in this class to read? Anyone? Thoughts? Or maybe you're reading, so I'll keep going. I will teach linear programming probably on Thursday, so just in case you're wondering. Imagine your Friday self reading this. So what do you all think? So I am willing to allow some slack in the sense that if you, it might be difficult for you to say, okay, if I'm writing it for my peers, you know, maybe a low opinion of your peers, you would put so many citations and just explain stuff that it gets to be too long. Or maybe you think that they know everything, you don't put any citations in at all. I think expecting the reader of this report to be, you know, let's say my grad students, so maybe not me, but someone who's been trained in this for a little bit. So maybe someone between the class level and me would be a reasonable target. So you don't have to be too detailed, but you need to provide enough information for the things that matter. I could have said here, for example, oh, you know, well, everyone should know what a semi-definite program is. You know, I'm not even mention that. That wouldn't work. Because those are words in the title that you have to understand. If you had trouble understanding what that is, then you should put it in. And I think ultimately that may be the best test. If something that you did not understand, put it in. If you understand it fully, then don't. Of course, you could then send me a blank report saying I understood this paper fully. So that will not work either. But what I'm saying is that if you go through the paper, if you're having trouble with something, write it down. You will find that writing it down helps you as well. Not just a report, it will help you. And if you're worried at the end, oh my God, how am I going to fill up 10 pages? Just writing down explanations of these things will actually get you pretty far along the way. And it'll help you understand what's going on. And, you know, who knows, later on you might go back and read and say, oh, no, okay, I understand what a semi-definite program is, but I actually wrote my own notes for this and now I understand. Does that answer your question? Any other questions? So again, yeah, so sorry. So once you're done with that, then you have the second last page, which is your references. And these things are generated automatically for you. So as long as you put, you know, use the format I showed you into things, then you'll be fine. If you need to find actual entries to put in, Google Scholar is your friend, and DBLP. I'll put up links to those two sites. We've never used them before. They have the right exact text to put into a file, so you can compile everything and make it work. You know. Any final questions? Yes.
Something I'm curious about with the background. So let's say the paper is old problem but new analysis or new approach.
Yeah.
So is it, like for instance, let's say the old paper said, or let's say a previous paper has said, this solution is within 50% optimal, and the new paper says, we have a new approach that's 75% within optimal. Is it necessary to understand the old approach that was 50% within optimal?
It depends. Is the new approach building on the old one or doing something completely different?
If it was doing something completely different.
Then maybe not. You should mention it, you should cite it, you should say, okay, there's this prior work that did this site, right? But do you have to go into detail on how it works? No, probably not. Yeah. You will need, again, for example, it turns out this particular paper, what it's doing is, it's taking the results from this other paper, number 5. Okay? So the result of this paper basically says, take your semi-definite program, throw your magic wand at it, it becomes really a lot more complicated, and that somehow gives you a better answer for certain problems. So they say, okay, we need a semi-definite program first. This paper has a semi-definite program for this problem we want to solve. Let's look at their semi-definite program, apply our magic trick to it, and we get our answer. Okay? So in this case, they are building on this other work. So this paper actually explains in a fair amount of detail what this other paper is doing. And that's something that you might need to do as well. In your example, that doesn't seem to be the case, so you wouldn't need to do it. So it really depends on what is needed to understand the result. And that's where your sort of plan and your thinking goes into play. What is the path to understanding it? You don't understand everything, but there are certain things you need. Without them, you will not be able to complete. Other questions? No? Okay. All right. So that's all I have to say. And again, I have the PDF, the LaTeX, and the BibTeX as samples, so you can take a look at them. This is all given here. And again, if you haven't run BibTeX before, you may need to do this like 4 times in the beginning. So it's a chain of dependencies that needs to be resolved. So it's working. There are ways to do this automatically. If you have some kind of more sophisticated IDE for writing LaTeX, then they do all of this automatically. But okay, let us continue then. The other thing I want to note is that, and feel free to groan at any point in time in the next 5 seconds. Wait, where did homework 2? Why did homework 2 disappear?
It went down in the project.
Oh, there it is. They went to the project. That's not
Somebody
right.
changed.
Oh, really? You're going to play that game with me now? I don't think so. Okay, sorry. I don't know why it has to do this crappy ordering. Okay, yeah, feel free to groan at any point. That's the homework 3 approximations. There are 5 questions. There, thank you. And yeah, well, enjoy. That's what office hours are for. The next assignment after this will be flows, and there will be one more assignment after that. I think that'll be it. And of course, the project. Okay, let us get to today's lecture. So we've been talking about flows. We've been talking about all kinds of, we've talked about the basic flow construction. We've talked about modifications you can make to the basic flow framework. And we've talked about applications that you might be able to convert to a flow formulation. So let's do another application today. So let's say, and this is again, this is in the notes, you can take a look at it. So, so this is what is called project management. You have a number of jobs that need to be performed. So put little circles to the jobs. Okay. So this is job A and this is job B. Jobs have dependencies. Right? So if I put an edge from A to B, this means that A okay, this is a little odd. Give me a second. I'm not even sure how to fix this problem. Okay. Well, A depends. Fine. On B. Okay. So in other words, if you need A to be performed, you need B to be performed as well. You can't do A before you do B. So there's no Jobs have profit. So this job here, interesting. I have to write small. This job here has a profit. So let's say the profit is equal to 5. So if you do it, you get 5 points. This job here is hard. It takes a lot of time and the payoff really isn't that much. Its profit is -7. In other words, if you do it, you actually pay for it. Some jobs you get a profit for, and net, the amount of work you put in versus the reward is large. Some jobs, that's not the case. Okay. So every job has either, has some number, which is either positive or negative, indicating a profit or a cost. Okay. And the goal here, is to, so let's say this is a set of all jobs. Okay. So P is a function from J to the integers, let's say, and it could be positive or negative. And the goal is find some subset of J, we'll call it the selected set, such that the sum over the job in S while making sure that you satisfy the dependency constraints. Does the problem make sense? So again, I have a collection of jobs that have dependencies between them, some number of dependencies that's given to me. Every job has a score that's either a profit or a cost, positive or negative. Your goal is to find some subset of jobs to solve. I mean, you could try to do all of them, but that may not be the best thing to do, right? Because maybe some jobs are really, really costly, and you want to avoid them, right? And therefore things that depend on them. So you want to find some subset to maximize the profit. Yes.
So does B have to be completed before I start?
Yeah, so the one way to think about this is that if in your selected set, if you put A, you have to put B. Because there's no way to do A without B. Time is not so much the issue here. You're just saying, okay, you can think of it as, I come in the morning, I'm going to plan which things I want to do. So that's it, I want to plan to do all these things. And then I'll figure out the right order to do it. That's not the problem we're solving here. That's a different kind of problem you can think about. That's not what we're solving here. Right now, we're just making the decision of which problems you want to even attack.
And then, do we assume the profit of A is independent of the profit of B?
Yes, that is correct. They could be plus and minus. One could be, it could be that B is so costly, you don't want to do B, and therefore you can't do anything that depends on B. That's a decision you have to make. Does the question make sense? Okay. Pair up groups, 2s, 3s. Just think about this 5 minutes. The goal is convert this to a flow. Discuss.
Okay. So we have parents from A and B or whatever. I'm guessing there's going to be a source.
Convert this to a problem.
Like there might be A and C that both could be maybe A and B.
Yeah, but I think you can improve it. I think the one over there on the desk is the projection, the black thing there.
So some are yes, some are not.
I think they use that for that one.
exactly.
Oh, okay, over there. They put another one.
There's no controller for zooming in.
Okay. There should be, because Vivek used to use something similar to that in his class.
And this room.
No, the other room.
But are they all? What about the one that's not problem 5
I don't see anything there. I don't want to fiddle right now.
But I think actually the video on that one will be much better. Since this is very close, the slides are like slammed. But that is why that will be a very strange one.
Well, that might be good for the video, not for the class.
Yeah, for the video. Next time, if I get it early in the next lecture, then I'll try it.
So I guess the flow for each one has to be like so it breaks up to have 1, 0, or 7. Now, A and B are going to have profits too. All of them. So,
okay. So, first question. As always with these problems, you have to first decide, okay, is it a flow problem or a cut problem? Of course, they're the same, but it's helpful to think of it one or the other. Is this a flow problem or a cut problem, do you think? And how would you go about even thinking about it? I mean, how do you make the decision? It's not a coin toss, right? So, what do you think? Yeah?
I would guess that it's a flow problem because we're trying to maximize something.
Good. It's a flow problem because you're trying to maximize something. Anyone else have a different thought? Yeah?
I feel like it might be a cut problem because we're trying to partition this percentage off to do instead of
Good. It's a cut problem because you have a partition set of jobs to do or not. Okay, now we do. These are both valid interpretations. And the annoying thing about the cut formulation is that you're not really trying, you don't want to maximize things involving a cut. The annoying thing about the flow formulation is I'm trying to select vertices, not edges, not trying to assign neat edges. So, if you weren't sitting in this class and I hadn't just said, figure out a way to make it a flow, you might wonder, is this really a flow problem or not? And you'd be right in wondering that. Of course, you know that because I'm telling you to do it, there must be a way to do it. But we're not sure at this point, right? And so, anyone else have any thoughts on which way to go here so far, based on what you've been saying? So, yeah.
I was just going to say, I mean, flow to me suggests like we have like some limited number of, like water flowing through the pipes or something.
Yeah.
And, here I'm assuming like we're assuming our workforce is unlimited in the sense that we can do as many jobs as we have to.
Yeah.
So
So you're still leaning towards the cut formulation, even though you don't want to deal with the max problem.
right, leaning towards that.
You're leaning towards it, okay. This thing is important to keep in mind that, the first thing you almost want to do with these problems, and you'll see this in the homework as well, is that you have to make some kind of, semi-decision about whether you want to go the cut route or the flow route. Again, you don't know ahead of time which is going to work. But it's best to make some guess and go that way for a while and see if you get stuck before you back up and go the other way, right? And this is the first kind of question you have to ask. And once you decide which way you want to go, then you proceed with that. So, so for the people who think this is a flow problem, what do you do next? If it was a flow problem, you have to figure out what?
What's in the sink?
You figure out what's your source, what's your sink, what are your edges. That may be obvious, may not be, depends on the problem. And what your capacities are going to be. You've got to figure out all these things, right? So anyone who has been trying to go that way, any thoughts on that? The flow direction, how you do it? Do you have any thoughts on how since you suggested a flow idea? How you'd get a source in the sink and capacities?
Yeah, so firstly, for the profit, I would split all the vertices into like an in and an out node, so I would have like that.
Okay, so that's good. So let's make a new page here. So let's write this down. Okay. So what you said was, so you want to split, so you say it again, you want to split a node into, so you take a node, it has some profit, and you want to convert this into what? In and out?
In and out, yeah.
Okay, and then do what?
And then whatever the profit is would be the weight of this edge.
Do you mean capacity?
Capacity, yes.
So C of E is equal to P of V. Okay, good. So let's call this V in and V out. Okay, all right. And I assume you use the graph that's already there, the dependency graph?
Yes.
Okay. All right. You have this all set up. Now where you have a source in the sink, are they connected to anyone?
Yeah, so any like job that has no dependencies,
Okay.
then I would connect that to the source, so the source would go into a job with no dependencies.
Suppose they all have dependencies.
Not sure.
Because suppose your graph looked like this. And so on. Then what do you do? Okay, so the idea you had was connect the source. Why did you want to connect the source to things with no dependencies?
Give me a direction to start.
Give you direction to start, because things that have no dependencies are things you can pick for free. Is that what your idea was?
Basically.
Okay, and therefore, and you wanted to use the profit as a kind of a flow measure. Is that the idea? So you want to push flow that counts profit in some ways.
Yes.
So the idea was somehow you would push flow that contributes to profit, but you're pushing flow through a vertex, so we know how to make that into an edge, so you convert that. And in fact, since we know that, you get to say, well, let's assume the vertex has capacity P. And from previous lecture, we know how to convert this. We don't have to do it explicitly. That'll be fine. And then you push flow to that, and if you can push a lot of flow, you've picked up a lot of profit. And if you start with the vertices that have no dependency, then I presume you connect T from all the vertices that what?
Do you have dependencies?
Okay, so other vertices do have dependencies. So fine. So you'd have some that don't have and some that do have. So that would look like okay, there's a direction issue there, but maybe this way we're flipping the arrows, because things that have no dependencies are pointed to by things that do have dependencies. So your graph kind of would look like this. You have things that do have dependencies, things that don't, and all the edges kind of go this way. Right? So then if you connect the source to this,
It would be up the...
yeah, I think you may need to
Yeah,
it
yeah,
wrong. Yeah,
right.
so let's just make this a T, and maybe this is what you intended to do, right?
Yes.
Okay. So now you have to push, now what's the capacity of the edges going from the source to these nodes?
I can't decide if it makes sense to pick one or infinity in this case.
Pick infinity. That was a good guess. If it doesn't work, you can change it. Right? Let's assume it's infinity. Okay. So it's all infinity, and what about this? This is also infinity? Yes. Right? Okay, and then you want to find a max flow in this. Okay, so the question you have to ask yourself, and I have no idea at this point whether this is the correct answer or not, and please feel free to tell me if this is correct or not or whatever. The point is not that. The point is, how do you figure it out if it's correct or not? right? So you've constructed something. You're claiming now that a max flow in this graph will solve the problem of picking a set of nodes that has high profit. So first of all, once you run the flow, how are you going to extract that set?
It's the vertices.
There's a natural way to extract a set of vertices from a flow. How do you do that? If I take a flow and I run max flow, there's a natural set of vertices associated with it. What is that set?
Isn't it dealing with the paths?
Pardon me?
Dealing with it.
Not quite. There's the whole max flow min cut relationship. How did we get the cut from the flow? Do you remember? So when does the flow algorithm stop? When you can no longer reach the sink, right? You can no longer find augmenting paths to get the sink. At that point, if you then say, okay, who can I reach from the source? That's a natural set. It's called the cut. It's called the min cut associated with that flow. So you could do that, for example. You could say, okay, let's take everything now at the end of the flow that I can reach from the source, but otherwise I cannot reach. So you're going to get a bunch of things that may be here. Maybe you'll get some things here, and you're claiming this is your answer. So, one second. So now you have a complete reduction. You have a way to transform your input into a flow problem, and you have a way to transform the resulting output back into your language. You have completed the reduction. That's step one of any solution to the flow problem. Step two is going to be, is this correct? And step two is two parts. Is it correct going from your problem to the flow, and is it correct going backwards? In other words, if you have a solution to your problem, will you get a correct solution to the flow problem? If you have a correct solution to the flow problem, will you get a correct solution to your problem? You had a question?
Yeah, just wondering, so if the profit was negative, if we just flip the direction of the edge and take the absolute value.
Don't ask me, ask him. What do we do if the profit is negative?
I would flip the edge, that would be mine.
Flip the edge, that's the solution. Okay. So, yeah, good. So we have a fully specified reduction. We now have to prove this correct. So what do you think? In other words, to show that this is a correct reduction, let's do it one way. Assume we have found the maximum profit subset in the problem. Will we find it here in the flow? So in other words, let's mark off in the flow problem. So we have the flow problem here. So I'll draw it a little bit bigger here. So we have source. We have this whole collection of things that have... By the way, notice that there's still a problem with this. As I said, if your graph has no nodes that have no dependencies, you can't even start this process, but we're ignoring that for now, because maybe you can fix it later. I don't know yet, right? So we're just exploring. But there is a problem to be fixed. So let's say you have all these nodes that do have dependencies in them, so we'll call it D. And you have all these nodes that don't have any dependencies. So all their edges are coming from here, right? They have no edges between them, otherwise they wouldn't be in that set. And you have T. And we look at the solution produced by the original algorithm, by the original problem, the project selection algorithm, which says, oh, let's pick here, let's pick this, let's pick this, let's pick this, let's pick that. Can we show that this corresponds to a min cut, or the set you get from max flow in this graph? What do you think? So I don't know the answer. I mean, this is the first time I've seen this algorithm. I have no idea how this is going to work. So maybe this will, maybe it won't. So we have to now imagine the flow. We're going to push flow through these nodes. We're going to find this max flow, and somehow we have to argue that this set corresponds to a good set. One way to think about that, in this case, I'm thinking on the fly here, is to say, what is the corresponding profit achieved by when you do that flow? So can we work that out? So we did the flow, we computed some subset. Can we figure out what the profit of this set is? How would we do that? For example, could it be, and this, I don't know if this is a good thing or not, could it be that Vi from a node is picked to be in your cut, but Vo is not? Could that happen? And it could, right? You could have a set where you had an edge here, and Vin was picked. Do I pick V or not then, as part of my project set? We don't know. It's not clear to me what to do in this case. So we're kind of a little bit stuck here. We're not quite sure A, how to interpret the result of the flow because of this problem I just realized about 2 seconds ago. That if you have a V and a V out, they could be on other sides of the cut and you won't know which one, whether you should pick it or not. Even if you figure out a way to solve that problem, we're still not quite sure how to assign cost or approval. So let's put this aside for now. I'm not saying it's wrong, you said we're stuck right now, so let's put something, yeah.
I just want to also say, I mean, it doesn't look like we have a way to guarantee that the flow actually equals the capacity.
Why is that?
Well, I'm just not seeing any constraints.
You're saying you don't know if the flow will yeah. So that's the other thing, right? We want to model this profit as flow, but the flow doesn't have to match the capacity. So we might push a flow through this vertex pair that is not equal to its capacity, which means you're getting partial profit, which is something we weren't really allowed to do in the original problem. These are issues we will have to resolve if we want to take this algorithm any further. And again, I'm not saying it's wrong, I just don't know. Okay? And in fact, I would encourage you to think through where we get stuck and what you might have to do with this, because for a lot of the questions on the homework, you'll get stuck in the same way. And the question is, are these unfixable problems or are they fixable problems? But having put that aside, just for purposes of pedagogy, let's look at the other way of thinking about this. So some people had said we should think about this as a cut problem, not as a flow problem, because you're picking a subset. Of course, there's a whole maximization thing that makes things annoying. But anyone who's wanted to use the cut formulation, how would we proceed? So let's say we want to use a cut formulation here. So let's pick a new page. Anyone want any takers for how we might proceed now? So if we want a cut formulation of the problem, what do we need? So we want a graph and cut. We still need a source and sink, right? We still need capacities. That has not changed. So what are going to be our source and sink capacities in the case of thinking about a cut? What do you think? Anyone? I know a number of people said they want to think it was a cut. They're not quite. You want to take a hack, Ian?
I was not advocating it. I was only suggesting.
Oh, to be contrary. No, I'm sorry. that's too bad. No, that's just no. What do we do next? Let's say we do want to go with the cut. What do you think?
I mean, I feel like at some point you have to model the constraints between problems, between, like, you have to do some project before some other project.
Did we not do that in the other formulation?
No, we did, but well, we tried to do this one. But in this one, we have to sort of do it explicitly. I think we should start there.
Yes?
Well, I was just going to say, so I was thinking about that problem where the flow might not equal the capacity.
Yeah.
So I don't think this would be polynomial time, but you can come up with all the possible job do, and then you just have the source go to one of those, and that goes, then that goes to the sink. Then you can guarantee that or maybe that's an approach.
So you look at all possible job orderings or job subsets or something like that.
Yeah.
And you're right. This would not be polynomial time because it would take weird exponential time or something like that. But it's still useful. You can just think about, okay, so if I had all the job orderings, maybe I could check something with them. Then your question would be, okay, is there a way to go through the job orderings without actually going through them? And a lot of good algorithms come from that precise intuition. You start with something really horrible, you try to fix it. Like, maybe I don't actually have to go through every single step.
Yeah.
So again, I don't know, but that's something that's worth thinking about. Maybe that's the way to do it. But in this cut formulation, if you want to encode constraints, think of it this way. What would be bad in our solution? What would be a really bad thing that we're not allowed to do in our solution? What are the constraints? Anyone? Yeah.
We couldn't have, like, we could say, like, if all the jobs were negative value, for example, we wouldn't want to pick anything.
Well, that would be a low quality solution, but would it be an illegal solution?
Oh, okay, yeah.
Is there any solution that's illegal?
A depends on B. You can't take A but not B.
If A depends on B, if we have an edge from A to B, and this is true for both formulations, not just the cut one. If A depends on B, you cannot pick A and not B. This is illegal. So whatever you do, you have to enforce this hard constraint. This is not a soft constraint. This is not like, I don't want to do it, so I will try it. No, you cannot do it. How would you enforce that in a flow problem? How do you force something not to happen in a flow problem? I mean, it's one thing to say we don't like it happening. It's one thing to say we'll give you, some penalty. But how do you just make it not happen at all?
Capacity 0.
Sorry?
Capacity 0.
Capacity 0 for what? The edge between them? So here's the thought, right? Yeah, go ahead.
You just combine the two in the same vertex, because at that point...
In the same vertex, you combine the two. So that you have to pick them both together. So now we have another problem. So that's a good idea, right? So let's try to combine them because that will somewhat eliminate the constraint. 1 second, that'll eliminate the constraint that we have. So now we can think, okay, so let's say we combine them. So let's try some examples, right? So if you have A going to B, you combine this into a node AB, and that solves your problem. Suppose you have A going to B, going to C. Well, you can pick C, or you can pick BC, or you can pick ABC. These are the allowed things you can do, right? So you might want to say, okay, I have a node C, I have a node BC, and I have a node ABC. And I can pick any 3 of these things.
Is that another problem as well?
Pardon me?
I thought of another problem as well. If something something depends on A, you combine the two, necessarily it depends on both A and B.
So can you tell me a graph that makes it happen?
So if like A depends on so A depends on B and C depends on A. That is
Right, so that's the same thing as we had. So there might be some way to do this. So maybe you can try to combine them in some way and then go through all possibilities. Things will start getting a little messy, for example, if you have, A going to B depends on C, then D depends on that, then maybe B depends on E. It might get a little harder, but maybe there's a way to work around that by creating these different subsets you pick. Okay? So that's another idea. This might be actually a way to deal with our job ordering issue. You combine these little blobs and maybe there aren't too many blobs. Okay. What's another way to do this? Another way is to go back to this idea of a penalty, but make the penalty huge. As Donald Trump would say, huge. So if you want to make it really, really big, what you need to do is think of it this way. If I'm in the cut formulation and I have a set that I'm picking, I guess I'm picking on the next page. These new projectors have messed my whole calibration. Okay, so suppose you have a set you're picking, right? And this is a set you're not picking. You want, what must be true is that there is no edge going across this, right? Because if there's an edge going across, that means you picked A, you did not pick B, but you were supposed to, right? Okay. How can I prevent this from happening? Think of this as a cut. What is the cut cost? It's the cost of all the capacities of the edges going out of the cut, right? If we're thinking of a cut formulation, that's how we measure the cost of a cut. Let's make this very good. Okay? So here's an idea. So for each edge I to j, set capacity equal to infinity. Okay? So I'm ignoring profits right now. Profit and loss. Okay, that's all well and good. That means now if I get any set, its cut, if it's finite, right, will satisfy dependencies. Okay? But what will the value of the cut be? Now remember, nodes have profits, right? So you somehow want to say something like, the profit of this set is the cost coming out of it, or something like that. And all you have at your disposal now are sources and sinks to play with. You don't have much else to play with at this point, because I basically eliminated any choice of capacities of these edges. What might I do? So here's an idea. I'm going to leave the graph the way it is. Okay, so I'm going to have this big blob of a graph. I'm going to add a source and a sink. And I'm going to add edges from the source to every vertex and from every vertex to the sink in some special way. This is my clue. What do you think I should do? So again, imagine that I add some edges from the source to every vertex. And now I compute a min cut. A min cut, not a max cut. And so there's some kind of cut here. Right? What is the cost of this cut? What is the value of this cut? The value of this cut is So let's say the set was, this was the selected set, this is the rejected set, right? The cost of this set is the cost of S R, remember we wrote it as this, is equal to what? It's going to be the sum of the capacities coming, all the capacities from S going to T and all the capacities from S going to R. Okay, so in other words, the cost of the set, and once again I've been writing too big here. Let me see if I can come up with it. Yeah. So the cost of the set is this, which is equal to the sum of all capacities of S of V belonging to S, V comma T, plus the sum of all U belonging to R, capacity S comma R. This is the cost of this cut. Okay? All right. Can I somehow choose now my values for these capacities that I have not chosen yet to make them look like the things I want to calculate? So let's look at the problem again and say, what is the actual profit? The profit is all the things we, is the profit of all things we pick, right? The total sum of all the profits we pick in X. That's our profit for the solution. If we claim that the solution is to pick S. How can we express it in these terms? What do you think we should do? Any idea? The clue is that I want to choose capacities from source to vertices and from vertices to the sink in a careful way to make this work. And someone want to make this to be some number that is small if the profit is large and that is large if the profit is small. How would you do that? Yeah?
Would you somehow say maybe in our original problem we take all positive profits and say this, if we add them all up, that's our potential profit, and then subtract everything from that number. So we invert it somehow like that.
So you're on the right track. So for example, suppose I were to say that the cost, the capacity of an edge from any vertex to T is its profit, if it's positive. Okay. So then this term here would capture the profit of all the things I picked. If it's positive, I can't put negative capacity in the right? Yeah. So what else can I do? So again, we're trying to build up to a possible solution. We don't quite know where we're going yet. But this seems like something that has given us something that's useful. But again, the goal here, again, is to keep in mind, and this may not work, is because I want this number to be large if the profit is small. Because I want to minimize something that works that way so that I can end up maximizing the profit. So what I want to do is express this function as something minus the total profit. If I can do that, then I have what I want. So let me see, let's see what we can do. Any thoughts? Let's take a 3-minute break. Think about this for a second. I want to make sure we get this right, because this is going to be something we apply over and over again. So let's take a 3-minute break. I have an announcement to make. All right, let's continue. Before we start, I have a quick announcement. Obed, you want to make an announcement? Yeah. Whichever you like.
So Goldman Sachs is sponsoring a hackathon this Friday. It's from 3 to midnight. The topic of it is going to be on data sciences, so you'll have a large data set to work with. And so food will be provided, pizza and soda and whatnot. So if anyone's interested, I posted on the Canvas discussion board the link for registration. So there's a 80 to 100 person max. We're working teams of 3. If you have a team or 3 people you want to work with already, you have to submit the application separately. Otherwise, the deal will be grouped up there. But it should be a pretty good event. I know there's a speaker coming in to talk about data science and whatnot. She should be there for the start of the event.
Maybe not the start. At some point during the day, she'll show up. Somewhere in the afternoon, she'll come and sort of take a walk through and see what's going on.
Yeah, the goal really is to work with a large data set and see what you guys can create with that. So if anyone's interested, please click on the link and sign up for it. So the deadline is tomorrow night at midnight for registration.
Right. So yeah, and the link will be on Canvas, so thanks for doing that. Yeah, it should be fun, yeah, and also just to add to that, this is part of this distinguished lecture that we have on Friday. The speaker, Catherine McKinley, is from Microsoft and UT Austin, and she will be speaking in the morning at 10 o'clock on dealing with uncertainty in sort of sensor devices and internet things. So it should be a fun talk. So it'll be in Web 12:30. If you can make it, that'll be a good time to come for that talk. All right. So back to our problem. Any thoughts, puzzlements, questions? Yes.
Well, one thought on how to turn a maximum into a minimum is you could take your maximum profit, you convert all of your profits by taking 1 plus your maximum and subtracting the profit of that node. Does that make sense? So you're inverting it and you're making them positive.
That's right. So you could do that. So in fact, that's right. So if you want to have a maximization problem, you want to make a minimization, you take some gigantic constant, some fixed number, and subtract everything from that. Therefore, minimizing the second expression with the C constant minus whatever.
And I chose 1 plus the maximum profit so that every number is greater than or equal to 1.
Right. Something very weird is happening here. Okay, hold on. Let's try to
I'm just still tripping up about what capacities to give from the source.
This is the essence of any sort of puzzle with flow. How do you figure out these things? So let's go back to this formulation again. Right? So we said that this expression is what we want to minimize somehow, and that should somehow contribute to maximizing the profit. So in fact, this was the wrong direction. If I use this construction here, this is going to contribute directly to that thing there. But I want to maximize this and I want to minimize that. So this is the opposite of what I should be doing. Right? So what I should be doing, in fact, is something slightly different. And so what we're going to... Okay. So what we'll say, so we said before, that the capacity of every edge I to j is infinity. We're going to say the capacity of any edge from S to V, okay, is equal to its profit, PV, if positive. And the cost of an edge from V to T is equal to minus of its profit, if negative. Otherwise, we don't add it. Okay? So there's an edge from the source to all the positive profit items. There's an edge from every negative profit item to the sink. And the capacities are, in fact, those profits, or negative, because you want profits. We want the capacities to be positive. Okay? All right. So the first question you have to ask yourself is, okay, so let's also define this fixed constant, which relates to what you were saying, which is C equal to the sum of all positive profits in the graph. So just add up all the positive profits in the graph. That's a fixed constant. Okay? All right. So now what is our cut cost now? Remember, our cut looked like this, right? So with an S, we have some set of vertices it picks, right? And we have the stuff we don't pick, just T, right? What is the value of this cut? So the value of this cut is the profit of everything in D. Why? Because there's an edge from S to every element in D, and its capacity is equal to the profit of the node. So the cost of this cut, so we'll write down the cost of this cut is equal to, let's see, S comma T, is equal to the profit of everything in D plus the cost of everything in S. Why? Because every node in S has a edge to T if it has negative profit, if it has cost. And we inverted the sign, so you just add them up. Is that correct? So the total cut value is this quantity right here. It's the profit of D plus the cost of S. Okay? What is this quantity C? C is equal to the profit of D plus the profit of S. Right? C is the sum of all the positive values. So it's whatever positive values you have there, whatever positive values you have here. Okay? Okay, so then what is, and this is the kicker, if I try to minimize this cut value, I will be maximizing this value here. What is that equal to? What is C minus the cut value? If you just substitute those two things, the profit of D cancels, right? So what do you get? You get the profit of S minus the cost of S, right? Okay, but what is this? What is the profit S minus cost of S? It's the net profit you get, which is what we want. In other words, even though we wanted to maximize something, and the min cut problem is to minimize something, you can get around that by doing this trick where you fix some large constant. You arrange it carefully so that some large constant minus the cut value is the thing you're looking for. So therefore, minimizing this will maximize that. And in this case, it all works out because this is exactly what you want. So by setting up the edges correctly, notice that you didn't really change the graph at all. You just added it in clever ways. And for a lot of problems, that's all you have to do. The graph or the problem is what it is, and you just add extra edges from the source and sync with carefully chosen capacities. And that gets you what you want. Yes?
I'm sorry, but what are those two S's there? Are they both edges from the source?
Sorry, I should have said this was capital S. This is the set of things you end up in the cut that you end up picking. Okay, so my new reduction, to go back to the problem of constructing the algorithm, right? The new reduction is, as I said earlier, which is this. That's it, that's my reduction. So my reduction is this, and return the cut. So my algorithm to solve the project problem is add capacity infinity to all edges ij, add new edges S going to V with capacity PV if it was positive, add edges from V to T with capacity minus PV if V had negative profit, run the min cut algorithm and return the cut you get. This is a well specified algorithm. Why is it correct? It's correct because we can prove it. If there is a solution, and we can show both directions in one shot by saying that the cut value you get from the flow problem is equal to C minus the profit you wish to achieve. Therefore, minimizing this is maximizing that is minimizing this. So I've done actually both things in one because I have an equality here. You're not always that lucky, but in this case it works. So 3 steps. Give the reduction, prove that the original problem yields the correct solution in the flow problem, prove that a flow problem solution yields the correct solution for the original problem. And then you're done. After that, you invoke your favorite flow algorithm and you solve it. That's what all reductions do. So that's the kind of thing you have to do if you want to take a problem and model this flow. You have to think through it in this way. You have to say, okay, what kind of tools do I need? Am I doing a flow? Am I doing a cut? How do I set things up? There's a lot of creativity and sort of, I guess, sort of systematic thinking that goes into this. But this is the higher level sort of template you have to use. Questions? And this trick is very useful, by the way. That sometimes when you want to maximize something that looks like a cut, you can make it a min cut. You can't always do that. In general, max cut problem is hard. It's NP hard, and the min cut problem is easy. But for certain cases, you can do it. And that's what flows. Questions? Yes?
I think we only care about the correct solution of the reductive version gives the correct solution of the original one. We don't care about the other.
You do, because you want to make sure your modeling is correct. So in other words, suppose that, so it depends on what you're going to prove. Here, since I'm proving equality, I'm essentially proving both directions at the same time. But suppose you have a flow problem where you say, okay, I have some problem, I map it to a max flow computation. And I say, if I find the max flow here, that'll give me the answer there. Okay? But it's possible that, right, so what you will show is that every flow here gives me a solution there. Right? If you can show that the value of the flow is directly related to the value of the problem, like we did here, then yes, your reduction is one way, but it's not only one way because it's inequality. In general, you'll show that a flow here gives you a valid solution here, and a valid solution here gives you a valid flow here. And only then can you make the conclusion that maximizing one is maximizing the other. Otherwise, you don't have that. In this case, I've essentially done both things in one. That's why it looks like only doing one thing, because of the equality. Right? They're exactly the same problem, is what I'm saying. That doesn't always happen. And then you need both directions. Okay. So you always need both directions. Some cases it is invisible because you can do it in one shot. Yes?
So what were the sets S and D?
The set that you, so S was the cut. So SD was the cut. In other words, when you ran the min cut algorithm, you got to set S as your min cut, SD cut, and then D was the other side of it. So the min cut is two sets, right? So you get the S and the D. S was the part that contained the source, D was the part that contained the sink. You selected and declined.
And then what part of this is enforcing the A depends on D?
Good. So can someone answer this question? How are we enforcing the fact that you never pick A without picking B? Can someone tell me this? Yeah?
And since we had marked the edges as infinity, the min cut algorithm wouldn't pick the edge A alone without leaving.
What would happen if you tried to pick A but not B?
Then the cut size would be more.
How much would be? Not more.
It is infinity.
Exactly.
So it won't pick them.
So it won't pick.
Yeah, to some extent, I thought those were capacities.
Sorry?
I just thought those were capacities for some reason.
They are capacities.
Are they costs? Or?
Yeah, that's a capacity. It is a capacity. But in a min cut problem, you're paying for the capacity, right? The value of the cut is the total sum of the capacities going across. There's no flow anywhere. Right? It's just a min cut problem. So this is the capacity. And so the point is that there's always a solution, right? Don't pick anything. It has some, the profit is not great, but it's something. Why would I pick an infeasible solution which has cost essentially, minus infinity versus a feasible solution? So it'll always avoid picking them because it can't. And because it would pay an infinite capacity if it tried to do that. Or it should essentially be infinite cost. It doesn't want to do infinite cost. And it wants to minimize the cut value, not make it infinitely large. All right. So we've seen a number of different ways of taking a basic flow formulation and generalizing it while still keeping the basic flow structure preserved. So for example, we've seen that so first of all, you can add, what is the first way we modified the flow formulation? If I recall correctly, we said that nodes can have capacities. Do you remember this? The way to create a situation where a node has capacity is to replace a single node with a capacity, let's call it, I don't know, C, not E. I don't want to call it C because C. Well, a node, okay, so node capacity, that's fine. Becomes two nodes, so what you were trying to do earlier, right? With a capacity CV between them, right? So we know how to do that. Edges can have capacities, that's the basic flow formulation itself. So you can actually make a little table. You can say things like this. So you can say, make two tables here, 2 by 2. So I'm going to put capacities here, and I'm going to put demands here. I'm going to explain what that means in a second. And we have edges, and we have vertices. This is our basic flow formulation, right? Edges of capacities. We just saw last time that you could put capacities on vertices. It turns out you can also have things like demands. What is a demand? The demand, so we know that for any edge, E, if it has capacity CE, we know that the flow on E is less than equal to the capacity on E. So this is a little known fact about oil pipelines, that they have to remain reasonably full. If they get too low in volume, the oil starts sort of drying up and sludging at the bottom of the tube and it causes blockages. I do not know this, but it's an interesting fact. So they have to maintain at least a certain amount of flow through the pipe at all times, while of course not bursting the pipe. In other words, not only do you have an upper bound on the flow, you might have a lower bound on the flow, a demand. Okay? Suppose you have this extra requirement that your flows must, at every flow, every edge must carry at least a certain amount of flow, as well as not carrying too much flow on it. Can we again transform it back to our basic flow formation? So again, think of an edge. So we have this edge here. It has a capacity C and a demand D. How might we make sure that this edge, in any feasible solution, will carry at least D flow, but I can still solve it using normal max flow? Because normal max flow doesn't care about, you could put zero flow on edge, it'll be fine. But that's not allowed here. How might you do it? So it turns out what you want to do is you want to kind of simulate the fact that you have D flow by doing the following. That if you have an edge that looks like this, you add an extra edge to a sink with capacity D, and you push an extra edge from the source with capacity D. Okay, and you do this for every edge, so you'll have a whole bunch of extra flow coming in. Yes?
Is demand uniform across all edges, or is it?
No, it could be different. So you could have a bunch of new edges coming into U for different edges coming out of it. And then you say, is there a flow that in which all the edges, these new edges coming out from the source and the sink, are saturated? Is there what is called a saturating flow? Okay. I only have a few minutes left, so I'm not going to get into details here. Maybe I'll talk about this quickly before next time before we switch over. But it's in the notes as well, so you can take a look at it. It turns out by doing the simple trick here, you can now take this new problem, just the way you transform the problem from nodes to nodes having capacities, you can transform this problem into one where now you run regular max flow, and it allows you to have demands on edges. And it turns out there's a similar way, which is even easier in some sense, to have demands on vertices. So depending on your problem modeling, if you want to say, well, I need to really require that I have a certain amount of flow going to this node or a certain amount of flow going to this edge, you can do that within the normal context of flow. So again, if you have a question on a homework and you say, okay, I want to model this problem as a flow problem and I will model it this way and assume that I have demands on edges, that's okay, because we know how to do it. Okay? I'll say a little bit more about this next time. The vertex demands on is actually much easier. You just have to add a new super source and connect to all the vertices and add a super sink and connect to all the vertices and do it. You can read that in notes. And next week we'll start talking about linear programming, which is kind of the basis of why these things kind of work. Okay? All right, so I'll see you on Thursday, and you have the report due on Friday. Yeah.